All right. Good morning, and thank you and welcome back. Join our lectures. And several quick announcements. First of all, the exam have been made, and I have uploaded them to the Canvas. You probably won't be able to see them. If you can see them, that would be bad, so let me know. And like I said, there are several versions of the exam, and not everybody have the same exam, and they're quite different. So I don't think you want to work together as a group because you might end up having different problems. Now the exam time is from 1 o'clock to 4 o'clock tomorrow afternoon. And I have, practiced the exam myself. So what I got is I finished all the exams and each individual version of it within an hour, actually much less than that. We're talking about half an hour in terms of calculation per se, but that's just me, right? So probably take you a little bit more time to finish that. But even that, everyone will have 3 hours of time to finish the exam, which should be sufficient, okay? Now, regarding to the exam type, we have talked about it. We will have, as it is right now, 3 problems per set. And among the 3 problems, number 1 will be multiple choices or filling the blanks. Number 2 and number 3 will be 4 worked out problems where you have to provide the whole solutions and all that. And for the full workout problem, I want to see partial solutions. That is, if you have time, which you should, draw the strain, stress, and internal force diagram, and that gives you partial credits, all right? And that is very important since we're, how to say this, we only have 3 problems. If you don't have any partial credits, it would be very bad for passing the exam, okay? Now, let me say this again. In terms of format or in terms of write out, the problem I showed you in the exam have like workout pages, but you don't have to use that. Just write all your solutions in a separate sheets you have, and we'll upload them. I want you guys to upload the original problem set that you're assigned to. This is very important, okay? Let me say this again. I would like you guys to upload the original problem set that you are assigned to, because everybody might have a different exam, so I have to know which one goes to which one when grading. So if you did not upload the exam set that assigned to you, and it's going to be very hard for me to find out which problem you're solving, and then it's going to hurt your grade. Okay, I'm sorry for that, but you have to upload the original problem sheet that you're assigned to. I mean, I have my own ways of find out which set you're working on, but it's just best for all of us to do that. Just help me grade. Okay, so that's all we have. And in terms of content, we talk about this. It will cover from what we have learned so far to last week, Wednesday. That is design for singly reinforced section, but not design for doubly reinforced section. And even for design for singular reinforced section, most likely you will be given the section geometry. When I say given section geometry, what I mean by that is width is determined. Now the height, you have worked on the homework, you should know that you can pick a height based on the span length. And as long as your height is within that range, you don't have to work to revise the height anymore during the solutions. Okay, so that's very important. All right, so if you don't know how to do that, please practice. Okay, all right, so any questions about the exam before I continue with today's lectures, guys? Questions? Are we all clear on this? All right, good deal. Okay, so let me come back to the lectures, okay? Start recording. This is on, share screens. Okay, let me do the screen sharing. All right.
Well, before we continue,
yeah.
Question 3 of the homework.
Yeah.
Like it doesn't tell us like a span length. How do we determine the height?
Yeah. So if you were not given, you can use 20 feet for now.
Okay.
For the span length, and you can determine height correspondingly. All right.
You mean 20 inches?
20 feet.
Oh, 20 feet.
Right, for the span length.
You're not talking about the height, are you?
I'm not going to give the height, but we're going to give you guys the span, and you have to come up with a height.
Oh, okay, I got you then.
Right, right, no problem. Okay. Any other question about the homework? All right. Okay. Well, let me continue. Talk about our lecture then. So what you're seeing, can you guys see my screen right now? Can I get a yes?
Yes.
Okay, good deal. Thanks. Sorry about that. So you guys should be seeing our last lecture notes. Okay. I just want to run a quick review. What we have done so far is analysis on the doubly reinforced section, design on a single reinforced section. And then we went on to explain how do we do design for doubly reinforced section. That is, again, the section geometry is given. We're just trying to find a reinforcement. So the difference between doubly reinforced section and single reinforced section is apparently the compressive reinforcement, right? So that is additional compression from the top bars that has to be considered. We also talked about, let me enter it and admit our friends here. And then we also talk about how we do that, right? So if you remember, we said since the only difference is additional contribution of the compressive reinforcement, all we have to do is that we first design as a single reinforced section, come up with a moment contribution of tension only reinforcement, call it Mn1. And then we utilize the applied moment or vis-a-vis factored moment to find out what's the additional moment required for the compressive reinforcement. Then we went down about how to find out the compressive reinforcement. Okay, and if you recall, we went through how to do this, and we also introduced a new concept called a reinforcing ratio. Let me find out where it is. Okay, that is called tension control reinforcing limit, or rho TC, and rho TC by definition equals to ASTC. That is only the tensile reinforcement only divided by BD, okay? And equal to this much. And you can see that this is related to the strain distribution in the section where 0.003 is the compressive strain for failure for concrete, and 0.005 is the tensile strain, a tension control limit for reinforcement, okay? So again, sorry guys, I have to admit these folks comes in a little bit late. And then once we have them, we can bring them into the equation trying to find Mn1. That is the moment contribution from the tensile reinforcement only, okay? Now, the difference between the phi Mn1, which is a contribution of the tensile reinforcement, and applied moment, Mu, which is the factor from the dead and live load, is the difference. And that is Mn2, right? That is the addition contribution from Mn2. So how do we determine Mn2, right? Simply, we use the difference, which is Mu divided by phi and minus Mn1, okay? And with that, right, we derive at Mn2 equal to As prime, Fs prime. That is the compression force of the reinforcement, compression force of the reinforcement on top, multiply distance between the tensile reinforcement and the compressive reinforcement to get additional moment. Okay, and then we utilize that to find out the required reinforcement area, As prime, for compressive reinforcement. Okay, and then we went down selecting bars and end up with the section like so. All right, and if you recall, there's a trick that we have to be mindful is that when we select the bars, right, we have to take consideration where there's a correction to be made. That is, you have to balance part of the tension force, right, with the added compressive reinforcement. If you forgot, you can go back to the recorded video and the lecture notes to understand, okay? And then with that, we finalize the bars for tension and compression side, okay? And last time, we left with you guys with a section that has a bars set. We set 4 number 9 bars for AS, which is a red bars here, okay? This is 4 number 9s. And 2 number 9s for compressive reinforcement on the top, and this is 2 number 9s. And the distance from the top compressive bar is 2.5 inch away from the top fiber, and the cover for the bottom bar is 2.5 inch from the bottom cover. Okay, now this is the section which is 14-inch height by 40-inch wide section, and essentially right now we just have to do a analysis of doubly reinforced section. Okay, analysis of doubly reinforced section. Now, I believe we have gone through examples of how to do analysis of doubly reinforced section. If you still have no clue, please go back to lecture 5 and 6 and watch the recorded video and go through the notes. Okay, now I'm not going to go through this derivation or analysis process again, but I'm going to leave it as a quiz number 4. Quiz number 4. And this is for you to practice. Okay, so what is quiz number 4? Let me state it clearly. Quiz number 4 is to find out MN and phi for a section of 14-inch by 14-inch with 2 number 9s on top, 4 number 9s at the bottom, with concrete cover 2.5-inch on the top and concrete cover 2.5-inch at the bottom. Okay, so all you have to do is provide the calculations for MN, which is the nominal flexure strength and stress reduction factor phi. Okay, so this is quiz number 4. Okay, quiz number 4, and this is due next Thursday. Okay, not this week. This is due next Thursday. Okay, quiz number 4. All right, and I will try to provide solutions for this after the lectures or after this due date through the recorded videos. Okay, we still need to make up 1 lecture. Okay, so I try to record a video between now and next Thursday. All right, so this is quiz number 4. All right, and then we have gone through the exam review last time, and we talked about basic properties, basic information about testing, and the singularly reinforced section analysis, doubly reinforced section analysis, winning stress block, and then we talk about how we going to have design of singular reinforced section. That is, again, like I mentioned before in the beginning of the lecture, given section geometry already. And last but not least, bar detailing. Yes, sir. Yes, sir.
Would you mind scrolling up to the quiz again?
Which one? Here?
Quiz number 4.
Quiz number 4. Okay. So you can find this from our file folder. I believe I uploaded already. Okay. There's nothing new. All right.
All right. Thank you.
Yeah, no worries. So here, I want to say one more thing about the bar detailing. Okay. It is the several things. Eventually, we're trying to find is beam minimum, the minimum beam width. And now, not only that, but when you do the calculation, I want you to also show me if you have, well, this is for the exam, okay? If you have multiple layers, right? Multiple layers. Be careful on the difference of clear spacing equations, okay? Why I'm saying that, I believe in the vertical spacing, there are 2 terms, right? Larger of 2 terms. For the horizontal spacing, this is larger of 3 terms, okay? And find out what's the difference, all right? And then I also want you to be mindful that you will come out with 2 minimum beam width. One is through the calculation we showed last time, remember? Now we have given you the clear cover and give you the bar size, so on and so forth, and tell you spacing between the bars, right? And that is one way to do it. That is just directly calculated, right? Remember, there's a gap as hat. And if you have to write the solution to it, I want to see the process, okay? So provide as hat. Even for multiple choice and filling in the blanks, if needed, please provide your process. This is how it goes in the usually grading process. If your answer is right for multiple choice, sorry, nothing I can do for you. But filling the blanks, if you provide the process, and if the process shows that you just have a calculation error, I will try to give you partial credits. But for filling blank problem, if you don't show your full workout, just give me a number and that number is wrong, then I'm sorry, there will be no credits to be given on that. All right. So for the filling blank problem, you also want to show full workout to gain any partial credits. Okay. All right. So for the beam spacing, coming back, you can do the actual calculation to come up with one number. And you can also refer to textbook table A5 to find the beam spacing with number of bars and size of bars as well, right? Now, you may ask, now, Bob, which one should I go for? When you got this calculation, the BMIN, B minimum, and the number from the textbook, whichever is smaller should dominate. Okay, whichever is smaller should dominate. Okay, That is to say, if in the exam, you just pick up the textbook number, okay, and tell me this is it. But if I compare this number to my calculated number, turn out that my calculated number is smaller than yours, right? Sorry, shouldn't smaller. Sorry, my bad. Okay, my head's not working right today. Sorry, bigger, okay, larger of 2, okay. If turns out my calculated number is larger than the table given number, then I'll go with my calculated number, okay. So that is just to tell you that it is best to calculate it regardless, okay, for the exam. Now in the design process, this is usually fine, but for the exam, I want us to do the calculations, okay. Now, a lot of you have done from the homework, give me a number, especially homework number 4, just from the table A5. That is not what I wanted, okay? I want you to guys run through the calculation and don't give me the reason that, you know, Bob, there's a table, why don't I use it? Yes, you will need to use it and learn how to use it with a lot of practice down in the road when you become an engineer or designer. But right now, since it's a lecture and a course and exam, we need you to understand why and how this was derived, so you have a good understanding of it. So please show me the full workout so I know you have a good understanding of it, okay? All right, so this is it, a quick review, okay? And I want to jump back to our main lecture. All right, again, this is just a Zoom link. I put it here in case I forgot. But again, let's talk about what's going on, right? So far, we have talked about the analysis and design for singly reinforced and doubly reinforced section. But you notice that all of the design we have talked about so far are under the condition that the geometry is given, which means you know the section, we know the width, and we know somewhat the height, right? We can pick it. What if we don't know the section, right? That is actually more of the case. So let's talk about today design of singly reinforced section. Singly reinforced section, okay? With unknown geometry, okay? With unknown section dimension. Now this is very rare, okay? But it happens. It happens. Okay, it happens. All right, now there are 2 objectives, right? First objective, we need to understand, we need to understand the definition, of reinforcement ratio, okay? Reinforcement ratio. Now you probably have seen this in our last lecture when we talk about the rho TC, but this is a little bit different, okay? So just to tell you right now, this is defined as 3 lines, defined as reinforcement area, AS. Now this is tension only, okay? Be careful, this is tensile only. Divided by BD, okay, BD. And this B is actually BW, or the minimum beam width, okay? Why? Because for a section like a T-beam or like an I-beam, you're going to use the web for B, okay? And again, D is DS, all right? Not DT, means effective depth, all right? So that is the definition of reinforcement ratio. Okay, we need to understand that. Second thing is we need, of course, learn to design with unknown section. Now, folks, I cannot read the chat message live right now due to this iPad thing. So if you lose the connection, you cannot see it, let me know, okay? If you do not see anything or you have any problem hearing, let me know, okay? All right, if not, I'm just gonna keep writing, okay? So these are the 2 objectives for today, all right? So first thing first, let's take a look at the design approach, right? So what are we doing here essentially? Okay, so I want to show you the section, right? This is the section that we've been dealing with so long. And we have reinforcement at the bottom. Let's just say 2 bars for now. And we have a depth of the section, call it DS. Width of the section, B. All right, and then we're trying to get the strain distribution, remember? And that is for concrete to fail, epsilon Cu equal to 0.003 at the top. And we have an actual compressive zone C, and mindful, this is C, not A, okay? And this is epsilon S. In this case, only one layer, so equal to epsilon T. All right. And then for the stress, right? For the stress, and we have the Whitney stress block. Since it is Whitney stress block, now the effective compressive zone, this is A. And mind you that A equal to beta 1 C, where beta 1 is a coefficient only dependent on the compressive strength of the concrete. All right. Now the magnitude of this block here is equal to 0.85 F prime C. Okay. And we know that we have tension. So this is a tensile reinforcement stress equal to Fy and yielded. All right. And I'm just drawing the distribution when it's yielding for singular reinforced section. All right. So again, this is strain. This is stress. And for the internal forces, we have a total compression from the concrete equal to 0.85 F prime C AB. Okay. And we have a tension equal to AS Fy. And the distance between them, we talk about this, ds minus I divided by 2, A divided by 2. All right, so that's it. Not complicated, right? Not complicated. All right, so here, we need to learn how to design it. If we don't know B, don't know ds, okay? So how do we design it? How do we design it? All right, now think about it. What is the biggest problem if we don't know the section, right? Now, if we don't know the section, we don't know the compressive zone C, and we don't know the compressive zone A, and we have no idea what is the moment capacity, right? So to do that, right, there's a trick. That is, we can actually set, okay, this is very important, set epsilon T to be 0.0075. Okay, 0.0075. Now, why this number? All right, first of all, this number is bigger than 0.005, which is tension controlled, okay, which is bigger than that. So I want to ensure that I'm in a tension control limit. Second of all, this number, right, is a little bit larger, much actually larger than this. It's not like 0.06. Why is that? Because we will have to recompensate it once we find out the section, recalculate this number. All right. So given that we are almost sure that this number at the end, after we give it the section, will be smaller than this initial value. So we're going to set a high strain for design. And we call this a design state. Design state. Okay, so this is something we set at the beginning, design state. Now, with that is set, right, we assume a certain strain and tensile reinforcement, and we can then just calculate the compressive zone now, isn't it? So that is 0.003, which is epsilon Cu. Well, you know what? Let me just write symbols first so you'll see it straight. So this is epsilon Cu divided by epsilon Cu plus epsilon T. Okay, and this is multiplied ds. Multiply ds, right? Now, bring all the number in, C equal to 0.003 divided by 0.003 plus 0.0075. All right, and again, you may ask, where does this number come from? We just assumed, all right? And then multiply by ds, okay? And end up, this is equal to 0.286 ds. 0.286 ds. Okay, now you see that I haven't given any actual numbers for the depth nor the width. I just assumed that the string gonna stretch to 0.075 for the tensile reinforcement, and went through and get my compressive zone size of 0.286 ds. Okay, and I'm gonna keep going. I say, okay, now the total compression from the concrete equal to 0.85 F prime C, beta 1 C, and this is A, by the way, okay? And then B. And now I bring this number in, okay? Which number? This 0.286 ds into C here, okay? And then I got a 0.24, okay? 0.24 beta 1 F prime C B D. B D. Okay, then now, since the strain is still 0.075, which is bigger than that, 0.05, which is tangent control, and naturally this is larger than yield strain of, for example, grade 60, 0.00207, isn't it? So I know for sure now my tension T equal to ASFY. And to keep the balance, this tension ASFY should equal to the compression from the concrete and equal to 0.24 beta 1 F prime C BDS. Beta 1 F prime C BDS. Okay. All right. So why do I need this? Why do I need this? Because now I can start making manipulations. How? Look at this here. On the left, I have ASFY. On the right, I have this. Okay. So it would be nice if I can come up with the reinforcement ratio index, right? As we introduce little fellow here, right? Into the equation. Why is that? Because I'll simplify my design approach. How? Let me show you, right? So notice this. What I'm going to do is I'm going to move this fellow. I'm going to keep this fellow on the left-hand side. Okay. I'm going to move this fellow here, BDS, to the left. So from this manipulation, I end up with AS divided by BDS on the left, and right-hand side becomes 0.24 beta 1 F prime C and divided by Fy. Okay, divided by Fy. All right, so on the left, this is what we know, the reinforcement ratio rho here. Reinforcement ratio rho here. Isn't it? Okay, so now rho equal to 0.24 beta 1 F prime C Fy. So what happened? What happened is now I have a rho, okay? I have a rho, which is reinforcement ratio, meaning the area of steel that provided to the section, that is an equation of beta 1 value and F prime C divided by Fy, which has nothing to do with geometry anymore. Okay, which has nothing to do with geometry anymore. All right, now why this is powerful? Because now I can just talk about how much reinforcement I need to put it in the section per area ratio. I don't have to worry about the geometry because I don't know the geometry. And I'm going to use this to eventually back out the geometry. How? This is how. Okay, so knowing this, right, I say, look, here's another important assumption. Now, not assumption, approximation, right? So approximately 0.24, right? Roughly equal to 0.25, roughly equal to 1/4. We're civil engineers, right? We're not so hang-on the details, right? But we're just trying to make it efficient, right? So 0.24 is roughly 1/4. Why that? Is because now I can call this initial design reinforcement ratio got equal to beta 1/4 multiply F prime C divided by Fy. This is what's important. Okay, this is for what's important. That is to say that we now have an initial design of reinforcement ratio. Okay, you guys still with me? Can you guys still hear me? Anybody give me a holler?
Yes.
Yep.
All right. I'm so worried about losing connection. Okay. So just let me know, right? If you're not hearing me or listening to me. Okay. So this is so-called initial design of reinforcement ratio. All right. Now this is very powerful because let me name it this 8.1, equation 8.1. Okay. Why is that? Because from this moment on, things become much easier. Because with this, I would say I will introduce another concept. You see a lot of concepts today. Okay. Let me introduce another concept called reinforcement index. Okay, reinforcement index, which is different, all right? Be careful. Now, the definition of reinforcement index is say, I'm just going to use another parameter or symbol omega here, all right? And I define that equal to rho, which is this fellow here, right? Multiply Fy divided by F prime C. Okay, and now that is equation 8.2. Okay, and just bear with me, right? You don't understand why, but just to bear with me. Okay, so with this new concept reinforcement index, what can I do? I would say, you know what? Recall. Remember when we do the moment, right? Mn that is equal to ASFY multiplied by ds minus half a. ds minus half a, right? So in this setting, we actually know that a, which is compressive zone size, equal to ASFY divided by 0.85 f prime c, okay, f prime c b. And my 8 here is weird, so let me correct that. Okay, right? So where does this come from? This is coming from T equal to C, right? Tension equal to compression. Okay, now watch out. I'm gonna play magic. I'm gonna say, you know what? I want to change the shape. So let me multiply a D depth divided by a D depth. All right, I'm just gonna multiply it something and divide it by something, right? This is 1, so it means nothing, right? But now with this equation can change. I can reorganize my equation, let it become AS divided by BDS. All right, multiply FY divided by F prime C, and multiply a D divided by 0.85. Okay, this I can do. This I can do. And now observe this equation. This becomes even funnier, right? Because now the first term is what we call a reinforcement ratio. What we call a reinforcement ratio. All right. And the second term, sorry, the second term stays. Second term, I don't know what it's called, stays. And the last term stays as well, right? No change. Okay. And now notice that we called this rho multiply Fy over F prime C omega. Remember? Reinforcement index, we just defined that 8.2. Okay, so 8.2. And now this fellow stays become D over 0.85. So A, go back to blue, A essentially equal to omega D S, S divided by 0.85. Okay, all right, you say, Bob, you just, making things, right? Manipulating things, didn't do a lot, right? This is where I start to show the reason for it. Now I can bring this back to my original moment capacity equation. Mn equal to ASFY multiplied by ds minus A divided by 2, right? Remember? And then Mn equal to ASFY, okay, bracket inside, ds minus omega d divided by 2 multiplied by 0.85. Just bring the in here. Okay, bring that in here. Then Mn equal to ASFY, collecting the terms, right? So I have a ds here, I have omega ds here, right? Collecting terms, so ds 1 minus 0.59 omega. Okay, this is what I end up with. And then finally, reorg, right? Reorg this term, and I got Mn equal to a omega of prime C, okay? 1 minus 0.59 omega and B ds squared. Okay, B ds squared. All right, and this is getting more interesting. Why is that? Is now I can observe this equation and I find out that this fellow here has nothing to do with geometry, but this fellow here is my section related properties. Section related properties, BDS squared. Okay, so now it would be nice, let me call this a reinforcement right? Reinforcement index. Okay. So no, this is, we call it omega reinforcement index. So sorry. Okay, we call this R. We call this R is defined as omega. This is reinforcement index. Okay, omega prime C 1 minus 0.59 omega. Okay, and this R fellow here. Sorry, Brendan here. This R fellow here is so-called flexure. Today's a lot of terminologies, okay? Flexure resistance factor. Flexure resistance factor. Okay, and we call this equation 8.3. 8.3. So with this flexure resistance factor, I can now recast my moment equation. And Mn now equal to R BDS squared. You see how clean this one is now? R BDS squared. R is the flexure resistance factor, BDS squared is just the section related property. So this is so-called 8.4. 8.4. So how do I use this equation? This is how. Because we know phi Mn, which is a design flexure strength, has to be bigger or equal than Mu, which is the factored moment to the structures, right? So I bring this equation here, basically phi R BDS squared has bigger than equal than Mu. So BDS squared has to be bigger or equal than Mu divided by phi R. Okay, divided by phi R. Okay, now this is truly where the magic happens, because now on the left-hand side, this is called section geometry, isn't it? That's the size, width, and the depth. So section geometry. On the right-hand side, this is what? This is the moment divided by strength reduction factor and multiplied by a what? Reinforcement related parameters. And this R reinforcement related parameter is called the flexure resistance factor. Okay. And now I can go even further, right? I'll say now let the width equal to alpha D, where alpha is a number. What number? Ranging between 0.5 to 0.8. Okay, meaning that the ratio between the width and height has to be 50% or 80%. All right. Okay, so this is so-called design constraints to avoid stocky sections, right? Always end up something like this. This is B, this is D, S, and B over D has to be between 50% to 80%. Okay, if you apply this alpha constraint to it, and then the equation become alpha ds cube has to be bigger or equal than mu divided by phi r. And eventually now ds, right, has to be greater than equal than mu divided by phi r to the power of 1/3 alpha inside. Okay, now ladies and gentlemen, this is what? This is the requirement or design for the depths. Design for the depths. And I want you to remember this equation, and this equation is called 8.5. Okay, this equation is called 8.5. All right, so just for our purpose, for the design, we can always assume phi equal to 0.9 to begin with. Right? And ds equal to h minus 2.5, one layer still, remember? And equal to h minus 3.5, two layer to begin with. All right, so this is the concept. Okay, so quick recall. Okay, I hope I didn't lose you. It's a long process. Quick recall, what happens, right? So what happens is, I want to design a section. I don't know the depth. I don't know the width. I'm just going to assume there's a width B and there's a depth ds. And I'm going to make a further assumption saying the strain of steel has the yield and has a strain of 0.0075, which is much larger than the tension control limit. Okay, I bring this in to the strain distribution diagram, get my C in terms of ratio of the depths. Okay, and I bring all this in, let tension equal to compression, and come up with a new term or definition of reinforcement ratio. And that turns out to be beta1 divided by 4 F prime C Fy. Okay, so with this initial reinforcement ratio, I invent another term called a reinforcement index. All right, and bring this reinforcement index into the moment capacity analysis equation and end up with another form. And then to simplify, I call this form, the first term in front of this, a flexure resistance factor. And then eventually it become a simpler format, Mn equal to R BDS squared. Now, if I constrain my design to say the width and the ratio has to satisfy certain ratio proportions, and then I bring to the equation, and eventually I can find a relationship between the depth and the applied moment divided by the initial target reinforcement parameters and design proportions and the strength reduction factor. So this is how we determine the depth of the section without caring about the span length, but only knowing the applied moment, factored moment, that is. All right, so this is the new process of design unknown section, but this is for singular reinforced section only. Okay, but all these are very abstract. So let me show you an example, right? So example 8.2, how to design it, right? So I would like us to design a simply supported beam. I would like us to design a simply supported beam with applied moment mu, that is equal to 153 kips foot. Okay, and I tell you the span length, L equal to a 28 feet. All right, 28 feet. Okay, and now the concrete have a strength of 4 ksi, and steel is grade 60, right? Again, if you remember, this is 60 ksi essentially. Okay, so this is how we're gonna start design. All right, this is how we're gonna start design. So you have choices. If we have supported beam, knowing the width is constrained, I can start doing that immediately, but I have no idea, I have no information. All I know is I have to constrain my height of the beam first. And from the past notes, we know that H has to be L over 12 to L over 18 by the ACI code. And I got to find out H is essentially has to fall in between 19 inch and the 28 inch of height. So I just have to make sure my final design falls in this range. Okay, but I cannot determine it. I cannot determine if the width is no, I can pick a number and go, like we said before last lecture, but I don't have a width, right? So I'm going to come from our instructed procedure today is what about initial design of reinforcement ratio, right? So rho initial as defined before equal to beta 1 is not defined again, sorry. This is just the equation beta 1 divided by 4 F prime C divided by Fy. Okay, and then this is 0.85 divided by 4, and top F prime C is 4 ksi, bottom Fy is 60 ksi, right? So I got this to be a number of 0.0142. A quick question here, does my rho have any unit? This is very critical, okay? The answer is no, it is unitless. All right, the KSI cancel KSI. 0.85, no unit. 4, just a numerical number, no unit. So no unit for rho, okay? Just a ratio, right? And with that, I can come up with a reinforcement index that is equal to rho initial multiplied by Fy divided by F prime C. And you probably guessed by now, this is 0.014, and this is 60 KSI divided by 4 KSI, essentially cancel the previous number. So this is essentially equal to 0.21. 0.21. And again, B21 is also unitless. Sorry, let me get this student here. Unitless, okay? Omega reinforcement index also unitless. Okay, also unitless. All right, now R, which is a flexure resistance factor, would equal to omega F prime C and multiplied by 1 minus 0.59 omega. Okay, so bring the number in 0.21 multiplied by F prime C.
What does R stand for again?
I'm sorry again?
What does R stand for?
R, where's the R? This one here, right?
Yeah.
This is called the flexure resistance factor. Did you catch it from previous notes? Here, let me show you here.
Okay, all right, thank you, thank you.
All right, no problem, no problem. Here, R equal to 0.21 multiplied by 4 KSI multiplied bracket inside 1 minus 0.59 and omega again 0.21. All right, now this you end up with a number of 0.736, but be careful, I do have unit for R. So let me just note here, R has unit. And the unit is same as the unit for F prime C. If you use F prime C as PSI, you end up with PSI, okay? That's what it is. So this is R. All right, so now I know R, and then I say, assume alpha equal to B over DS. Remember, that is a ratio, and that has to falls between 0.5 and 0.8 range. And then I say, you know what, let alpha equal to 0.7. No reason, just love the number, right? Alpha to 0.7. Then what I do, I can use that equation, which is ds, remember, larger equal than mu divided by phi alpha r, this is over long, and 1/3 power. Okay, so ds has to be bigger or greater than 153 kip foot, that's the mu, and I want to convert everything back to kips inch, so multiply 12 inch per foot divided by alpha 0.7, that is assumed, phi 0.9, again assumed, r calculated 0.736 KSI. And that's the reason why I want to convert everything back to kips inches. Okay, now you calculate this, you find out ds essentially has to be bigger than equal than 15.8 inch. Okay, and I love this number because now I say choose let ds equal to 16.5 inch. Right, you say, Bob, why don't you let it become 16? It's 15.8, you know, it's just 16. No, I want to add this 2.5 because remember, h equal to ds plus 2.5 for one layer, ds plus 3.5 for two layers. There's 0.5 here. I want to make a wholesome number for my height, remember? Okay, so that's the reason, right? That's the reason. And now h for one layer still ds plus 2.5 inch, okay, equal to 16.5 plus 2.5. I end up with 19 inch. And because I love a wholesome number, so 19, just a little bit odd, so I'm just going to set h equal to an even number, 20 inch. 20 inch. Okay. All right. So this is 20, right? This is 20. Notice that I've changed it. I've changed it. Because, you know, this is the initial design and ds equal to 16.5 and now pick 20 inches. So let me do a section evaluation. So this is 20 now. H equal to 20 inch. Okay, H equal to 20 inch. But how about B? I still don't know B yet. It's about, wait a minute, you said B equal to 70% of H. Yes, I did say that, but you know what? I used the number to get 16.5 inch, but now I'm picking 20. I changed everything again. So now I'm going to set H and find B again, right? So find B. How do I find B? This is how. Now the DS actual equal to H minus 2.5 inch. All right. So I gotta use 20, right? Instead of 19. So 20 minus 2.5 give me the actual depth. Oh, I don't like mixing unit. So sorry. Okay, this is 17.5. That is my actual depth. Okay. So to do this, right, I need to do this. I need to set B, D as actual. Okay, squared has to be bigger or equal than mu divided by phi r. And now my B has to be bigger and equal to 9.1 inch. All right, 9.1 inch. So I will say now set B equal to 10 inch. B equal to 10 inch. All right, finally, and I'm finishing up, okay, before I let you go. Finally, I have my section, which is B equal to 10 inch and the height equal to 20. And don't forget, okay, the reinforcement ratio initial still set as beta 1 over 4 F prime C over Fy, okay? And that is how you provide AS over BDS. How you determine, next step, you can determine AS now. Okay. All right, I'm gonna stop here. This is good stop. So next time we're gonna follow through and trying to find AS from this. But this is the general procedure if we were not given section geometry and to find out section geometry. Okay, it's gonna be a lot to take in.
Exam tomorrow.
I'm sorry?
Is all this going to be on the exam tomorrow?
I don't think so. As I mentioned several times, what we'll be covering exam, you can go back to the beginning of lecture, recorded lectures, and find out, okay? This is not gonna be on the exam, okay?
Thank you.
Yeah, so this is how we design for unknown section geometries. A lot to take in, so I want you guys to take some time understanding this, all right? So for the time's sake, I'm gonna stop here and I'll answer any questions you have, okay? Folks, any question for me? You're welcome to ask right now or stay behind.
Could you go back to the very bottom, right where you were wrapping up?
Yeah, give me 1 second, okay? Let me just share my screen. Okay. Can you see my screen?
Yeah.
Is this where you want?
Yep.
Scroll higher, or this is the end of it?
Yeah, right there. It's fine.
I have a question about the bar spacing from their the review exam review.